EOR for Mature Oilfield Development. This video is based on Professor Babadagli's presentation delivered as part of the SPE Distinguished Lecturer Program. Let us first start with a question. What exactly is a mature oil and gas field? Here is an example of the typical production life of a field. Can you guess at which point, marked by a red question mark, would be considered the time that the field has reached maturity? Did you guess it correctly? Mature fields are fields reaching the peak of their production, or fields in declining mode, and fields that are reaching their economic limit after primary and secondary recovery efforts. Now that we have defined a mature field, why are mature oil and gas fields important? This chart shows the number of oil and gas giant fields that were discovered since 1868. There are around 30,000 oil fields in the world, and the total number of reserves amounts to approximately 150 billion cubic meters. 33 of the remaining giant mature oil fields contain about 50% of the remaining oil. This means that additional reserves are from existing fields and not from new discoveries. Now we know that these mature fields are critically important for future oil demands. How do we develop them? And how do we optimize this development process? In this video, we will discuss three major points. Number 1, estimate. The estimation of remaining reserves using various data collection tools and techniques. Number 2, EOR for mature fields. We want to look at the EOR methods used in mature fields. For EOR for mature fields, we must first diagnose and understand why there is unrecovered oil in the first place. Number 3, then come the reservoir management strategies for majors, independents, and national oil companies. We want to look at the efficiency of tertiary recovery methods, and we want to determine when is the correct time in the development period to switch to the tertiary method. Estimation. Correctly estimate the remaining reserves using various data collection tools and techniques. To estimate the remaining reserves, we want to determine the amount and location of the residual oil after the primary and secondary recovery using core analysis, logs, reservoir engineering or simulation, production data, chemical tracers, and well testing. So why do we want to estimate? Let us compare the calculation methods of remaining oil saturations and their results using 32 fields. We can see that the well-based calculation results are consistent in the case of logs and production data. However, reservoir-based calculation methods, such as material balance, display a larger residual oil percentage. Therefore, there is a need to combine all these calculation methods for better accuracy. Let's look at these estimation methods a little further. In comparing the remaining oil saturation techniques, we can see that the average ROS values from core, log, and tracer tests are smaller than those taken from the material balance calculation. And the ROS values from pulsed neutron capture and resistivity techniques are equal. SOR from a single well tracer, on the other hand, is lower than the SOR calculated using logs. Now, to understand the importance of using a correct estimation technique, let's look at this field case in the Yates Field of Texas in the USA. The Yates Field was discovered in 1927 in West Texas, and 1.3 billion barrels have been produced since the beginning of its production. It's a strongly heterogeneous mixed wet carbonate reservoir, and there are 1,100 producers and 57 injectors dated in 1992. Any resistivity-based saturation models depend on accuracy in determination of M and N. In the Yates field, a resistivity-based saturation model was challenging due to the fractured and vuggy nature of the reservoir rock, which is a common characteristic of carbonate reservoirs, resulting in M values ranging from 1 to 5. Along with these variations in space, we could also observe the variation in time for N. In addition, electromagnetic propagation tools also do not work well in gas. Therefore, the solution to the challenges met in the Yates field was NMR, nuclear magnetic resonance, logging, which is insensitive to gas. And it was found that NMR-based approach is simple and can even be implemented at the well site. Here is a case in Libya. For reservoir evaluations, the traditional logging techniques could not yield dependable answers, and therefore, there was a need to use a different logging measurement method. A new tool called CHFRP was applied for deep formation resistivity logging through metal casing. Then they could obtain the accurate reservoir monitoring results from the cased hole formation resistivity log. The results showed that by applying an efficient remedial option, such as a cement squeeze of the previous upper perforations and reperforation in front of the oil column in the upper reservoir, there was a significant oil improvement from 34 to 253 barrels per day, and the water production shut off from 90% to 0%. As can be seen in the previous examples, a reliable in-situ measurement of SOR can define the target for enhanced oil recovery, or EOR, and also allow estimation of the potential bypassed oil in the field. This movable oil is the target for infill drilling and/or tertiary oil recovery. Since there is not an absolutely reliable model for predicting SOR, different SOR measurement methods can be used to evaluate a reservoir field. Based on the reservoir evaluation results, appropriate mature field development technologies can be considered. Technologies applied to revitalize mature oil fields are based on either well or reservoir applications. Once the maximum number of wells that can possibly be applicable to the field is reached, well development practices such as recompletion, stimulation, treatments, optimization of lift, recollection of data, surveillance, and new entries are considered. Next, injectors for pressure maintenance or displacement are drilled, mainly targeting secondary or tertiary recovery. So what exactly is tertiary recovery and why do we want it? How efficient is your current tertiary recovery technique? In this section, we will look at both lab scale and field scale examples. Now, before we discuss the examples, there are important things to consider before choosing a tertiary recovery. First, what is the company's cutoff limit for cost? Is it $10 per barrel? $30 per barrel? $50 per barrel? Second, what is your target? Is it residual oil reduction or is it the recovery rate? Usually, it's extending the life of a reservoir by displacing residual oil. There are three important things to consider before designing mature field EOR. 1. Core experiments to determine the potential recovery for a given EOR agent. 2. Proper formulation of chemical blends. 3. Proper sequence of EOR methods in case of WAG, or water alternating gas injection. Let us discuss these three cases. In the case of the Loudoun Field in Illinois, in the USA, after 38 years of water flooding, we can clearly see that surfactant flooding helped reduce the oil saturation by 5% to 20%. This is the lab study case, where 4 different chemical compositions were tested. Based on the slug sizes, the results varied significantly. We must consider the chemical concentration and also final recovery results in order to optimize the process. It is also critical to decide when to start these applications to maximize the ultimate recovery of oil. This is an important issue, especially for tertiary recovery applications, if the company is concerned with the ultimate recovery rather than accelerating the production rate in short term. In this case, with flue gas injection as water alternating gas, we should ask, should we start with solvent flooding or should we start with water flooding? The yellow line in the graph is a secondary slug and the blue line is a tertiary slug. As we can see, the difference in injection sequence has resulted in different recovery results. To investigate further on the importance of sequence on tertiary recovery, lab-scale tertiary recovery by solvent was conducted by our EOGRRC research team. This research is based on 3 previous major observations. 1. When solvent is injected into a previously water-flooded reservoir, solvent may invade only the water-filled pores. 2. Oil may not be displaced from the smaller pores. 3. A water film may develop between solvent, oil, and grain, as we can see in this actual experimental image. As seen from the microscopic images of earlier studies, it is highly critical to determine the sequence of water and solvent injection, and the sequence is determined by the wettability of medium. In a water-wet medium, recovery efficiency is not high. When solvent is injected first, followed by water, water displacement efficiency is not as good as the mixed wet case. The black color represents water followed by solvent. Blue is solvent and green is water. The routine practice in EOR is to start with water, followed by solvent injection. In water-wet medium, water sweeps well initially, but solvent displacement is not as efficient. As seen in the video, solvent tends to go to water-invaded pores rather than residual oil. Subsequent water flooding after solvent injection was not efficient to displace both solvent, oil, and their mixture. Water flooding is observed as in the water-wet case, but as solvent has the tendency to enter into the oil-filled space, it creates a good quality mixture to displace oil. Water flooding starts, and the subsequent water flooding is more effective than the water-wet case, as reflected in the recovery factor value. In conclusion, for both wettability cases, starting with solvent is effective, but the mixed water-wet case, starting with water flooding and solvent, can still be effective. Now, let's look at the field application examples to explain this concept better. EOR is a big field operated by a big company, while SAMA is a small field run by an independent company. The EOR field is a large field with 450 wells owned by a large company. It has long-term targets and high investment. It's a chalky carbonate field with light oil, a viscosity of 1 centipoise, and a natural water influx. We experimented with chemical EOR options in the lab. Blue bars show the water injection cases, yellow bars are the surfactant injection that came after water flooding, and the red bars are the case of surfactant flooding only. We can see the improvement in the oil recovery after the surfactant injection following the water injection, which is potentially due to the in situ low viscosity oil in water emulsification. It's advisable to start with water and continue with surfactant as a tertiary recovery method, but starting with surfactant alone is not a good idea. The SAMA field is a small field with 20 wells. It's managed by a small company with short-term targets and low investment. It's a sandstone field with oil viscosity at 1 centipose. It's defined by a natural water influx and has a depth of 3,250 meters. The two sandstone layers are characterized by a low permeability layer at 1 millidarcy, with a recovery factor at 10%, and a high permeability layer at 150 millidarcy, with recovery factor at 70%. Let's look at the EOR options of a small field owned by a small independent company. Can we extend the life of a mature field owned by a small independent company? Here's the experimental analysis. In the SAMA field, immiscible gas injection was carried out with nitrogen. We can see that when nitrogen was injected after the water injection, there was an improvement in oil recovery. Numerical simulation results showed that even with one converted injector only, field scale improvement is possible. The white line in this graph shows the most optimal case, and we can see that achieving 5,250 psi is definitely economically feasible. Here are the conclusive remarks for our video in mature field development practices. One should start with locating the remaining oil, then figure out proper tertiary recovery methods. For small companies, we may look for faster recovery, which is more short-term based. For big companies, we may look for higher ultimate recovery in the long term. And before field application, there should be lab experiments. We want to properly design injections, as well as understand the role of water or gas saturation history and the chemical compatibility between the injected solution to oil. We should also choose an appropriate time to begin the tertiary recovery, as the sequence can have a huge impact on recovery mechanisms and the final recovery results. You should also try to be proactive and forecast the impacts a few decades ahead and conduct accurate reservoir characterization for optimal designing purposes. Also, the human factor such as experience and expertise should not be undermined. We do not have the luxury of leaving 50% of oil trapped in mature and marginal fields. And by carefully selecting the design and also designing the technically and economically viable techniques, we can maximize the full potential of our mature reservoirs. Thank you for tuning in, and for more information, you can check out the papers listed here or throughout the video.